let's do that. Okay, yeah, nice. Now we're recording. You might have gotten a pop-up. Hopefully you got a pop-up that says you're recording. I don't want to, um, you know, invade your privacy or whatever by recording and you don't get a little pop-up. Hopefully you did. Okay, cool. So here's the deal. So this week in class, we talked about, so this was, let's see, the week of, I don't know what day it was the week of, whatever. So we talked about chapter 5, which was if you're following along in the book, which in usual semesters we are, but I don't know, whatever. I don't know how much you rely on the book. I know in normal semesters, organic chemistry is a pretty book-heavy class, but no matter, right? So we talked about stereochemistry, and we did a lot of this review last week, right? So this is like a little bit of old news at this point, and like I said, you had the quiz. So there are some key ideas about it, right? And I'll mention those again, but I think I'm gonna stay away from going way too in depth about stereochemistry. I'll refer you to if you're here now and there's some stuff about stereochemistry that's still like throwing you off. I'll refer you to last week's workshop recording, or if you're watching this from a recorded thing, likewise, right? So there was kind of more of a thorough like explanation and review then, right? But there are a few key ideas, and they're most relevant, or they mostly pertain to when you actually have a chiral center, right? And so the main idea about a chiral center is, so we have like a hydrogen, right? And then we have something A and B, right? And now, oh, well, I already used C. That kind of sucks, right? Let's do Q and R, whatever, right? A bunch of different letters. I could have used colors too. That might have been a nicer way to do it, but that's okay, right? And these are all 4 different things. And then you know, when you take a mirror image of them, this is like, by now, I'm sure you've seen this drawing like 500 million times, right? You take this mirror image of it, and then there we go. And oh, look at that, right? There's an R. Okay, that's it, right? Yeah, these are, we would say, not super imposable, right? They are enantiomers because we took mirror images of them, right? So enantiomers are mirror image molecules. Okay. By this point, you know this, right? You took the quiz on it. Okay. So anyway, once you have this sort of thing, you can rank their priority. Of all 4 substituents, right? And then once you do that, you move number 4 to the back, right? And then from there, if you have 1, 2, and 3 this way, then the car goes right. Right, so that means it's R. Okay, right, and then if it's the opposite way, right, then the car goes left. That's not actually how it goes, but it doesn't go right, it goes left, and the only thing besides R is S, so it's S, right? Okay. So there's the standard trick, and then okay, so I actually looked through the textbook, and I didn't get a chance to go through the whole recording of the whole recorded lecture and see how he does it. But I remember when I took the course, they taught it in terms of E and Z instead of just cis and trans double bonds. there's like a minor and subtle distinction, which is that cis and trans double bonds only um those like only matter, I think, when you have the same things on either side. And E and Z refers to when you have anything on either side, right? So with so for double bonds, if you have like A and B, right? And you can have other stuff where like you can have other stuff like over here and here, right? But we're just looking at highest priority. Then these guys are enemies. And so they're E. Okay. And I just wanted to get rid of this dash. Okay. Yeah, so these are E, and then, well, if they didn't teach you E, then okay, this is what you could call trans, right? And then, well, if they're on the same side, then these are, I don't know, friends, so there's Z, right? It's another one of those situations where it's not E, so it's got to be Z, right? You just have to remember the mnemonic for one of them, and then that's it, right? Or some of you might call this cis. Okay. Yeah, depending on whichever way it was taught to you in class. Like these are very subtly different. E and Z is like more general, from what I remember, but it's minor. People really colloquially use cis and trans more anyway, so it's fine. Yeah, those were kind of the big ideas in chapter 5. Again, so this the worksheet that we have today, which we'll go through. The questions are mostly pertaining to stereochemistry, so it'll be a good review because this stuff like will haunt you. It always comes up. But well, we'll look ahead to reactions now, because those are, well, that's what's next, and this is where things start to get real. Okay. Now things are picking up. Like, as weird as it might seem, you kind of at this point have all of the skills you need to do the rest of organic chemistry. That's kind of crazy, to think that, like, well, that's kind of it, right? At this point, you start doing reactions. It's kind of true. There's a little bit more. I'm kind of exaggerating a little, right? You learn that little bit more in this chapter, and then after that, you're off to the races, right? You're learning reactions, and you'll be drowning in flashcards. It's like that's the usual way this goes. Okay, so here we go. Now, chapter 6, or what you're going to be learning next week. Sorry, I always refer to these things as chapters because again, it's in usual times it's a kind of book heavy class. Oh, okay. So someone asked, do these letters stand for a word? Like if R means right, does S mean something? Same for E and Z. So R and S, I can't remember, but I'm gonna guess that it's the same thing. I know for E and Z, they're the first letters of some words in German that mean like, I don't remember what they mean. I know Z is. I can't remember what. I know E and Z stand for something in German, and I'm gonna guess that R and S stand for the same thing, or stand for also something in German, but I can't remember. This sort of stuff, these like naming things, I mean, they came around in like the early 20th century or something, right? And that was a time when like Germany was real big in chemistry, or like the late 19th century. So I know that, right? R and S, I can't remember if they really stand for anything. if you know German, that's another good way to remember E and Z. But well, I don't, and I'm gonna guess that not a lot of you do either. So, um, yeah, yeah. I remember I saw that one time. I've seen what R and S stand for too, and I can't remember. Um, yeah, that might be another way to help remember it. Maybe I should look that up. Yeah. Okay. Well, anyway, up next, you are going to be learning a lot about reactions. Okay. And all right, well, this is a kind of useless description, so maybe I'll provide a little bit more context. Um, so you will be learning about, I would say, so to be more specific, nucleophilic substitution and elimination reactions. All right. So that is the focus here. I'll go through what those things actually mean. But just to kind of like give a little note and motivate why we actually talked about stereochemistry. From this point on, stereochemistry matters. Okay, right? Or like 5 minutes ago, I said that stereochemistry would haunt you, right? It's gonna haunt you now, and continuing on. You will like need to use what you've learned from stereochemistry to answer questions about this, right? So, to frame this in the context of things that you already know, and well, once you learned free radical reactions, stereochemistry already mattered there, right? You have, just to give like 2 examples that I came up with earlier, because these are good reminders anyway. So, okay, if you take like this compound, like some allylic carbon, right? You're going to brominate over here, right? But now, okay, this is now chiral, right? We brominate in the allylic position, but we get 2 of these things, right? So these are both chiral, but this whole reaction that you get out is racemic. Okay, because we have a 50-50 mix of this one over here and this other one. Okay, and maybe just to really drive the point home, like here's another example, right? Let's say we have this. Okay, these are now the sorts of questions that you're going to start seeing more and more as you get further in the course, right? Let's say we have this, and this is optically pure. We would say, meaning we just have this one enantiomer and not the other enantiomer. It's just this. Somebody did the work beforehand and selected out for that, right? And so, okay, we do the same thing, right? Well, there are 2 allylic positions here. One of them is already brominated. And well, we usually don't like brominating twice on the same thing. So it'll brominate on the other allylic position, but it can either go on the same side as the first bromine or on the other side, right? So, well, we can get something that looks like this. And what do you notice about this compound, someone?
It's a chiral meso.
Anyone?
The first one is a chiral meso. Because of the plane of symmetry.
Well, just to cover it, so this compound is actually meso. Okay, because we could draw this mirror plane through it, right? So, it looks the same on either side. So it's meso. Okay, and over here we get well, this compound is not meso. There's no way that we could draw this guy over here so that we have a mirror plane. So, well, this is just optically active, okay? Optically active, right? So this reaction is kind of messy because we get something that's like meso, something that's not optically active, and we get something that is. And that's a little bit ugly, right? But the point is that you've already seen cases where this where stereochemistry matters, right? Maybe it wasn't really emphasized yet, but it is. It kind of matters at this point. And yeah, and in these cases it maybe doesn't make the biggest difference. Oh no, okay, well, and I get, okay, yeah. And just to really bring home another point, which I forgot to think of this one earlier, but this is kind of an important idea. So let's say we have something that looks like this, and let's see, how can I make this chiral? So I want something that's chiral, right? So something that'll look like whatever, we'll just do that, right? Or make my life simpler. Okay, so here's this molecule. This thing is chiral because this carbon over here has 1, 2, 3, and 4. That should be a hydrogen, but it's number 4, right? I didn't rank them in order of weights. I'm just saying it has four things here, right? So let me get rid of those so it doesn't throw anyone off. Okay, so there are 4 different substituents here. All right, well, what if I do now? Okay, now I can use just bromine because it's not, there's no double bonds in this thing, right? So bromine itself is perfectly fine, right? Okay, and there's 1 tertiary carbon, and bromine is pretty selective, so it's just going to take off that one. But, and this is the important part, what we wind up getting is that some of the time that methane is going to stay up front and our bromine will be kicked to the back. But then some of the other times we'll get that the bromine goes up front and the methyl goes to the back. Okay. And well, these are enantiomers, right? And these are racemic.
Okay. Adam, just to go back to the second example that we did.
The reason I brought this example up, like kind of, last minute is, well, this is to say that the mechanism here matters. Okay, so not only are you going to have to look at stereochemistry, but you need to know how the mechanism affects the stereochemistry. Okay, so this is to say that the mechanism really matters here. And the reason in this case that you wind up getting this happening is that once you pluck off this hydrogen, you get a radical. And radicals are sp2 hybridized, right? sp2 hybridized things aren't chiral centers. Like, they can't be. So at that point, the bromine can either attack on top or on bottom if your molecule's laying flat, or it can attack from the front or from the back. However you want to put it, but that bromine can come in from either side. And so you can wind up getting this racemic mixture. And from now until the time you finish organic chemistry, people will be asking you, what is the product of this reaction? And tell me whether it's optically active, if it's racemic, if it's enantiomerically pure, all this sort of stuff. And you need to keep an eye out for that, and you need to think about how the mechanism affects what you get out at the end. Okay. Well, yeah, that's to say stereochemistry matters. But, well, okay, what did I actually say up here? So I said we're talking about nucleophilic substitution and elimination reactions. So this is the point where you have to start talking about nucleophiles. or let's say nucleophilic substitution. Okay. So nucleophilic substitution, this is the point at which we have something on a molecule, and maybe just to give you like a really nice and like simple, clean example, right? Let me draw it actually this way. So we have this carbon, and here is, sorry to interrupt. So the second example to further analyze would our products be diastereomers that can be separated via crystallization, etc. Yes, so these two are diastereomers because we flipped one of the chiral centers, but not the other. So you can separate them. In fact, these two will have different physical properties, right? So you can do, in theory, you could do crystallization. You could separate them out by like, other ways that you can separate out things that are chiral, right? In general, enantiomers are hard to separate. You need something else that's enantiomeric to separate it, right? It's kind of one of these like chicken and the egg things. Oh my God, am I not able to hear you guys? Okay, has somebody said anything? Can somebody unmute themselves so I can see if I can hear?
Yeah, before I was trying to ask the same question, but I didn't want to, I just thought it would be better to maybe type
Wow,
it
okay,
because...
I can like hardly hear anything. Let me see if this is like a Zoom setting thing. Let me stop sharing for a moment. Yeah, sorry, I was not able to hear. Thanks for letting me know. That is so weird. I might. Okay. Nidhi, can you try talking now?
Can you hear me?
Oh yeah, loud and clear. Okay. Yeah, that was on
Okay.
my end. Okay, thanks.
No, it's no problem. Sorry about that
Yeah.
for
Thanks for letting
interrupting.
me. So were other people, so I saw your question in the chat. Were you asking it?
I was, but then I didn't want to like keep talking and distract things for other people who were able to hear, so I typed
Okay.
it.
Okay. Yeah. Okay, yeah, sorry about that. I did not
No,
hear
you're good.
anything. Okay. So yeah, you can
Mm-hmm.
you can separate these things. And in fact, like with enantiomers, it's really hard because you need another enantiomer. And I was kind of leading into this, like it's kind of like a chicken and the egg thing, because then you brings up the question of how did they get the first enantiomer, right? Because you need
Right.
enantiomers to get enantiomers, right? To make, at least to make them pure. Yeah, but that's for enantiomers, but these aren't, right? Because these are not mirror images of each other. I am not sharing my screen anymore. Here we go. Now I am. Okay, there we go. Now you can see what I'm talking about. So these two are not mirror images of each other anymore, right?
Mm-hmm.
We flipped one of the chiral centers, but not the other one. And that means like these molecules are like actually pretty different, and they have different properties, so they'll behave differently compared to each other. So yeah, we can purify them. They are diastereomers, and we can purify them in like simpler ways than if they were enantiomers.
If you had, like, if you didn't have the second allylic position on that same second molecule, would it be possible for the bromine to like brominate by coming underneath that same position it's already brominated?
Yeah, in that case, it likely would.
Mm-hmm.
So there's this thing about like, so if you have a carbon and then you have like these two guys on the same position, right? And this is like whatever, this is whatever.
Right.
So these two are called geminal, if I remember correctly. There's also vicinal, which is I think if they're on adjacent carbons. Yeah, so there's something about like usually having geminal substituents is kind of like is kind of unstable. Usually things don't like being on the same thing. Like I know for example, something that you'll see kind of like down the line is if you have two alcohols on the same carbon, um,
Hmm.
they don't like that, and then they usually like one of them removes itself. Uh, for halogens, it's not exactly the same because they don't have like the same range of reactivity that alcohols do, but um, usually putting two bromines on the same carbon is kind of difficult.
Yeah.
Um, yeah. So if there wasn't that other allylic position, it would be well, it would be a bit weird. It's hard to say exactly what would happen.
Hmm.
Yeah. Here we go. Okay. There's another question in the chat. So,
Thank you.
mhm. Would the bonds be able to rotate on the optically active product um, and produce the enantiomer? Uh, let's see. So in this case, this optically active product, let me redraw it over here. So this thing looks like this, and then we have this one coming back. And so if we rotated these bonds over here, well, let me draw the mirror image just to kind of see what we're working with. Um, okay, so there's those two bromines, and then well, if we rotate this molecule around like that, um, like around this axis, uh, it's going to look exactly the same, right? Because well, this one is going to turn around to be into the page, and the other one is going to turn around to be out of the page. Um, so we can't like physically rotate the molecules. So they're okay. They are different molecules. That's when we draw it like that. Let's see. Can we redraw the bonds here, or can we rotate the bonds in a special way? Um, well, I'm redrawing the bonds, so let's see. So up to here, let's keep everything the same. We'll only work with one half of the molecule. And well, okay, there's the line we're going to rotate along. And why don't we rotate? Oh, this is going to get confusing. Okay, here we go. Why don't we, let's see. I mean, we could put this guy up here, and that would kick the bromine to be down here, and then the hydrogen to be back here. Um, but that's not super helpful, right? Um, yeah. So we can't. Well, we could rotate along this bond too, right? And this double bonded piece is just like a floppy like little tail, right? Like it can go up or down either way. Um, and we could rotate along this bond to do something useful, right? Uh, but well, we're not gonna do anything over here and over here because we're just gonna work with one half of the molecule. And the idea is that well, if we could rotate the bonds in some way, then we should be able to do it on just one half of the molecule. We probably shouldn't need to rotate both. Um, yeah, but I'm not seeing any way to rotate those bonds to make the enantiomer, and that makes sense because well these two should wind up being different. Uh, Different molecules. Enantiomers be products. Uh, no, only one of the two enantiomers would be a product. Um, and the reason is because we started with one of those chiral centers being fixed, right? So we started with one of those being optically pure, right? In this case, let's see, we could do the math out, right? So here we go. This is 1, 2, 3, and that's 4 back there, right? So this is an S. And so this carbon here will always be S, right? In this final product, it's always going to be S. And in this enantiomer, we know that over here it's R. Okay. Right. And what we wind up seeing, I think, is in this product. So over here, this is, let's see, 1, 2, that over here is 3, and this is 4, this hydrogen, right? And let's see, the arrow goes this way, but the hydrogen's facing us, right? Or facing us, facing you guys, right? So if we were to flip the whole thing around, then the car would be going left. So this is S. It's also S. Okay. Right. Yeah, so over here, this is also S, right? And then we can see what this is all about, which is that if we, oh, sorry, here we go. If we do a mirror flip of this molecule, then we get R and R, right? And no amount of moving or rotating without swapping anything on any of the bonds, we can't change anything about this molecule over here to be about this molecule, right? But we only get this one. Well, that is, we don't get this one's enantiomer over here because we know that this guy always has to be S, right? Same thing over here. It's also S, right? If we really want to go the extra mile, well, we know that this carbon over here is R, right? So this carbon we know is R because, well, it's the opposite of the one below it. All right. So these are the only 2 products that we get, right? It's worth mentioning this reaction here, with this NBS, it doesn't touch that carbon that already has a bromine on it. It leaves it totally alone. It pretends it doesn't even exist, right? So that carbon with the S is gonna is totally gonna stay as is.
If it were just Br2 instead of NBS, would it then like mess it up?
So this is like
Like they said that NBS was more selective, but I wasn't sure like how much that actually affected things.
So in this case, the reason that I haven't used NBS is because, and well, you're gonna see this fairly soon, not this week, but I think the following week. So when we have the reason we use NBS to do allylic bromination is because, well, it does exactly that. It does allylic bromination. Okay. Now notice I had to write racemic because from this point on, people are going to care. Okay, but when we do, let's say this, and then we don't even need heat or light, okay? We can just throw bromine in it, okay? You can add heat or light, but it's not going to matter. Bromine's going to do what it's going to do anyway. So what happens is this bromine will add, oops, let's not add another carbon. Oh my God. So what happens is the bromine literally sits on that double bond, okay? So this bromine looks like this, right? So what actually happens is that it just goes here and then it goes there. Well, I'm not going to draw the electrons moving yet because that's something that we'll deal with later. But this bromine just goes and sits on there, and this one sits on there. Okay. So the reason you can't use bromine whenever you have a double bond is because it's just going to do this instead. This is way easier to do than a reaction, a radical mechanism, right? This happens, it literally just, it sits on top of it. Okay. So
So it like takes away the double bond somehow.
Mm-hmm. Yeah.
So so the product doesn't have a double bond anymore.
Yeah. So instead of adding that bromine somewhere, it just sits on top of that. It just takes away that double bond, right? So if we have a molecule with a double bond and we're like, sweet, yes, I could do allylic bromination. This is the best thing ever, right? And then we add that bromine, it's just gonna do this instead. And this is not a super useful thing to get out, right? Like this is a, I mean, you will learn about this reaction here, but it's not that useful. You will learn about it in the context of many other much more useful reactions is the point here. Yeah. Okay. Oops. Here's this participants panel. There we go. I was just opening that up so I can have it on the side over here.
For the like the bromination without NBS and particularly substituting at the allylic position, would that mean that like solvent actually matters? Because for it to break the double bond, it would involve like I imagine it would involve the polarity of how bromine is partially negative and like the carbons are partially positive. So if you had like a polar substance, it would maybe actually become a part of the reaction mechanism.
So let's see.
Because usually we can just use like CCl4 or something. But like, is that why? Because you don't want something that's not inert.
Yeah, so in the case of like this reaction right here with this bromine, that is actually true. So this is a good question. And you will trust me, you will get all the answers you seek in I think 2 weeks or so. But yeah, so if we actually yeah, I guess the way that I drew it isn't exactly like super faithful to what happens because it kind of it does actually take place in 2 steps. So what happens is that we wind up getting like, let's see, so there's these 2 bromines and let's see, yeah, so it won't let me undo. That's annoying. Okay. So what should happen, and this is not necessarily the like most representative reaction mechanism. So this guy has some extra electrons and it goes on there, right? And these get kicked off. And so this is what this mechanism is going to look like. So we have this bromine and then we have this weird triangular thing, right? And this is like awful. And then, well, we take that bromine minus that we just made, right? And that's going to attack over here. But there's nothing saying that bromine is the only thing that can attack, right?
Right.
You are more than welcome to have water, right? Why can't water just go and attack? In fact, it can. And this is kind of a common reaction type that you will see shortly, right? So that is to say that this whole thing, right? This with a really ugly box. So this needs like an inert solvent. Yeah. Yeah. This is actually a case where, yeah, the solvent does matter, and this is a good question to have asked because it entirely relies on nucleophilic substitution here, right? In this water attacking or this bromine minus attacking, that is a nucleophilic substitution reaction. So what does that look like? Okay, this is what you'll be focusing on this week. So here we go. Okay, so let's say we have a carbon, and this carbon has, you know, let's say it has a hydrogen. This is another one of those pictures you'll be seeing like over and over and over again. Um, it's just like the standard organic chemistry picture, right? Um, oh, let's not a hydrogen. Let's put something else there. Okay, so here we go. C, and then let's use bromine, right? Why not? Bromine is a nice thing to have. Okay, so let's say then we have hydrogen and okay, I'm gonna, for the sake of like just preparing you for what's to come, we're gonna make this pretty general. So we're gonna have A over here and B over here, right? That's like super vague. We don't know what those two are. They could be anything, right? In fact, this hydrogen could be something else too if we really wanted, right? And what we're gonna do is we're gonna take something called a nucleophile, and I'm just gonna write it as Nu because it could be any nucleophile, right? And well, it's gonna go right here, and it's just gonna attack at that carbon, right? This is what we would call really standard as backside attack. Okay. All right. Well, cool. Well, what happens, right? There's an intermediate, right? So there's a point where we have nucleophile, and then these kind of like semi bonds between each of these, right? And everything else is flipped. It's in the middle, right? Okay. Everything else is flipped. And the standard analogy to use here, and this is the transition state, so I'll mark it with like this or TS, right? This is transition state. The standard analogy here is that it's like an umbrella that's flipping inside out, okay? There has to be some point where the umbrella is totally flat, okay? So this is our transition state, and then what happens is, well, this bromine is gonna pop off, right? It's gonna come off. And so what happens is we get this nucleophile, this Nu, right? And then the hydrogen is up here, and then this A is over here, and the B stays in the back. Okay. And what you'll notice is it's a little different. It's not exactly the same molecule, right? Because we swapped out that bromine for the nucleophile. But look at this. Look. Okay. I've drawn this picture for you over and over and over again, right? You've seen this like 50 million times as opposed to 1 million with all these other diagrams, right? These basically look like mirror images. Okay, with the exception of the fact that bromine becomes a nucleophile, or bromine gets swapped out for this nucleophile, right? That's the exception. Well, okay, so what we say is, well, okay, all right, this is a mechanism, right? This is a real like reaction mechanism. This really like this happens, and this is one you'll be seeing a lot. So this whole thing that I just drew here is called SN2. Okay, and that stands for substitution and well, it's nucleophilic is bimolecular. Okay, so there's the S, there's the N, and that's where the 2 comes from. Okay, it's a kind of convoluted name. SN2 is a lot easier and nicer to go with, right? So that's well, this is what an SN2 reaction looks like. Let me zoom out, give you the big picture. In this case, kind of literally. Whoops, I'm zooming all over the place. Oh my God. Okay, there we go. That's the right level of zoom. There we go. Okay, so this is an SN2 reaction. What happens is we get a nucleophile, it comes in, and it does a backside attack and flips the stereochemistry. And in the process, it inserts itself into the molecule. Okay, so this process has inversion of stereochemistry. Okay, that's what we got out of what we did there, right? Yeah. So this is what this process looks like. Okay. Let's break down all of these things, right? So okay. First, we'll break down all of the things in the name. So substitution. Okay. This is easy, right? Substitution. This just means you're taking a leaving group, and now we're going to go even more general, right? So this is a leaving group, which we'll write Lg, right? And then you're replacing it with nucleophile. Okay. So we're replacing. All right. Okay. So I've been saying nucleophile this whole time. So what does that actually mean? Okay. So a nucleophile is, well, if you know, I don't know, Greek or whatever this comes from, right? So so this is something that really likes positive charges. Right? The nucleus is positively charged, so it likes nuclei. I don't know. Okay. This is like the literal definition. It's not very practical, right? So I'm just gonna get rid of it. It doesn't tell you a lot about what it actually is, right? So in general, a nucleophile is something that is, so this is negative, or it has a lone pair. Okay, so that's one thing. So it's, yeah, it's negative or it has a lone pair there. It is generally small or not bulky. Okay, now we're actually doing reactions, right? So the actual how they bump into each other matters, right? If it's really big, right? If you have, like, let's say a negative charge thing right here, right? And it has this whole other huge rest of the whole molecule attached to it, right? It's gonna, that rest of the molecule is gonna bump into whatever else you have way more often than that little part of it that matters, right? Okay, and just to mention the last thing, right? The last thing that matters is that it's polarizable. Is usually like the last thing to care about, right? So again, this is also still really general. So what really matters here is to actually show some examples, right? So these are some really great nucleophiles. Okay, and this is kind of one of those things where, like, you want to know, you kind of want to be familiar with the list, right? Like, yes, you could use these three, like, you know, helpful rules to tell, but knowing this list is a little bit better, right? So for example, if you have HS minus is a good one. It's small. That sulfur is a pretty large atom, so it's like polarizable, right? There's a lot of like within, let me write the next one. So iodine is a like fantastic nucleophile. Actually, let me make this a bit more general. Let me say RS. As long as, you know, R is something that's fairly small, right? So you have iodine, right? And iodine is this huge thing, right? And, well, if it needs to, you can move all of those minus charges over here, and all those plus charges, not plus charges, right? But like you can kind of separate out where that charge tends to be, right? And so you can kind of make it something like this, and then okay, this is even better, right? This is like really, really helpful for doing this reaction, right? Because you can have all that negative charge in one place, right? And negative really likes positive, so that's going to make a really good nucleophile. It's really going to want to attack that carbon. Okay, here we go. Let's get rid of all the rest of this stuff. Okay, and here we go. Let's keep doing this table, right? These are like the real like pinnacle of nucleophiles, right? But then we have some pretty good ones. Okay, so bromine, right? It's like iodine, but it's just smaller, so it's slightly less polarizable, right? A hydroxyl radical, and in general, alcohols that have lost their carbons, right? There's a nitrile. Here's one that you might see rarely. It's called azide. It's an ion. Like you can make salts with it. Sodium azide is one. It's like super toxic, but well, we don't have to worry about that, right? So here are some that are like okay, right? So NH3 is an okay nucleophile. In practice, NH3 is actually, I'm gonna bump this one up. I'm kind of following from like a table, right? This is one of those things where like you write down the table and you kind of like remember it. I'm gonna say NH3 is a good one too. It's a pretty good nucleophile. Okay, so okay is chlorine. It's all right. It's not that good. I think like water is one that's okay. Or in general, some alcohols, right? And then pretty bad, but like we still write them just because I don't know, I guess they're relevant, right? Fluorine sucks. In general, fluorine's really bad at reacting with things. Are there any other ones that you might interact with? I don't remember. In the recorded lectures, there's definitely a table of these because like you have to see them at some point. And you should go along with that one. But this is generally like the kind of ordering that they go in. Usually looks something along these lines, right? So okay, this is really what we mean by nucleophiles is based on this, right? And then I should also just mention like if you have like or let me make this even more like of an explicit example. So OCH3 minus, right? So this is a better nucleophile, for example, than well something like O minus and then like tert-butyl, right? Like this is bulky, right? And it has what we might call steric effects. Steric just is a word that refers to size, right? Whenever something is big, you say like, oh yeah, it has steric effects, and then you're fine. Right? It just means it's bulky, it gets in the way, it kind of bumps into other stuff. Okay. And then so that was nucleophilic, and then the last thing that we had here was that it is it's not substitution, we already talked about that, is bimolecular. Okay, so that means so everything happens in one step. Okay, some people might say, well, I mean, if you want to get more into it, that kind of means that it has to do with the rate depends on the concentrations of both reactants. Because everything happens in one step, you need both things to show up at once. The counter example to this, and I dropped my pen, give me one moment. The counter example to this is SN1 reactions, which happen in multiple steps, but it only depends on the concentration of one thing at a time. Okay, so I'll show you what that means. in a second. Let me find my my pen. 30-second break. It fell on the floor. Got it. Okay. So everything happens in one step, and so this means so it depends on the concentration of both molecules. Okay. Cool. All right. So I've talked about this a whole bunch, right? And I've really built up SN2, right? Like the rest of the reactions, I should say, they do not have as much detail as I just put into SN2. And the reason for that is because once we've built up this terminology, the other reactions that you're going to talk about are, I mean, they come real quick, right? Like, so the only other thing to mention here is that before I just finish the rest of them in like 5 minutes, is that for SN2, what you have is in general. So let's look at like so like CH3X, right? Where X is a leaving group, right? Or we can say LG, right? So this is better. It will react faster than, for example, like a secondary carbon, right? And that is way better than, for example, a tertiary carbon. In fact, tertiary carbons will basically never react with SN2. So this is tertiary, secondary, primary. Okay. Or methyl, whatever, whichever one, right? Same thing. And it's because all these other carbons, you have to do backside attack, right? But it's really hard to do backside attack if there's a whole bunch of stuff that's getting in the way, right? Like if you can't actually make it to that carbon that's in the middle, like if you can't get to here, then well, it doesn't matter, right? It doesn't matter. You could have the best nucleophile there is, but it's not gonna help. And this is yet another one of those situations where in general, it's hard to say if these are if this will be better than primary, or if they're going to be better or like the same. The textbook or lectures might have details which say like whether it's necessarily better or not, but in general, primary will react very well, and then also will react very well are benzylic or allylic, right? And this is a weird situation, but it just has to do with like when you get in that transition state, remember, like way up at the very start, I talked about this, right? And the molecule goes flat. And there's something sticking up to something sticking down. Having those double bonds next to it is helpful because you can kind of like do a little bit of resonance, not quite resonance, but like you can kind of conjugate a little bit when you have this state and when you have a double bond next to it. Okay. It's pretty technical. It's like the actual reason why is like kind of complicated, but that's roughly it, right? So the point is benzylic and allylic are also really good for SN2. Okay, well that's SN2, but now SN1, as you might guess, it depends on one molecule at a time, so it's unimolecular. So for example, now this one's going to be good at tertiary carbons because let's say we have like a bromine, right? And why don't we put it in I don't know, whatever your favorite alcohol might be. Let's put it in ethanol, right? So what'll happen is, well, this bromine is just gonna pop right off, right? Because that tertiary carbocation is fairly stable, right? That's pretty nice. It's a tertiary carbocation. It's as good as it gets. Well, almost, right? Benzylic and allylic, as you might guess, also really good here, right? And then, okay, well, now there's an OH, right? And this is a decent nucleophile, right? There's a positive charge right there. So, okay, it's just going to go right there, right? Well, okay, there's a positive charge now there because, we have 3 bonds to an oxygen. But, well, we can finish this reaction off, right? Look, this bromine is just going to take off that hydrogen, and that's it. Okay? That's what SN2 looks like. So the idea behind SN2 is this happens in multiple steps, and it only depends. So we might say the rate only depends on the carbocation formation rate, on the carbocation formation. Okay. So that's the idea here. Okay. That's what it looks like, right? It's just, there's still a molecule with the leaving group, and there's still a nucleophile. But all that happens is the leaving group just comes off. It just decides it leaves, right? It just pops right off. And then you have a carbocation and a nucleophile in the same room, right? And you know what they're going to do, right? The nucleophile's going to stick right on. And that kind of does it. That's it.
Can you show the ending step again? Like just scroll over a little bit. Yeah.
Yeah. That's what it looks like. This ending step is like specific to the nucleophile that I used, right? So, for example, you can imagine a situation where I would have like, you could very well have something that looks like, you take this and you put it in hydroiodic acid, right? Or really, what really matters here is you put it with I-, right? And then, you get this plus and a bromine, right? And then this guy is going to come in here and finish that off. Right. Yeah. So if you have a minus charge thing, like this thing is just totally a minus charge, then you don't have to do this like extra hydrogen transferring step. That was just because I chose to use like an alcohol as the nucleophile. Yeah, so that just kind of has to do with the specific case. But that's the whole idea. Same things go, right? And I should mention, the reason you couldn't just do a backside attack on this molecule, right? You could not just go here and then, right? This is not allowed. You can't do this. And the reason is because, well, those methyl groups they get in the way. They're just way too big, right? They're not going to let that OH get into where it needs to go. It's not going to happen. Okay. So instead, you go around this other mechanism. Okay. And maybe just to make a last note, and I think right after this, I think we'll just do the problems from this week, right? But once this happens, well, there's nothing saying that this oxygen here, or this like ethyl oxide group, right? Like there's nothing saying it can't just do the same thing, right? It can't just come off and the bromine will just pop in instead, right? Just to say, these are all equilibrium. right? And equilibrium means that, well, we're never going to get 100% out because some of it's always going to stay behind. All right. There are ways to get around that, right? We know that there are ways to really push the reaction in this direction, but well, those are finer details that well, we're not that worried about the practical side of things in this class anyway.
Is the iodine also equilibrium?
Yes.
Okay.
Yep. Yeah. It's just because there's just another one of those situations where there's no reason the iodine can't just decide to come off. Yeah, either way will go. One of the two sides will like naturally be favored because like this CI bond is probably more stable than the CBr bond, or it might be the other way around, right? So one of the two sides will naturally be more favored. So SN1 is kind of like a weak mechanism. It's not that great, right? You lose a lot of the product. You have to do some funny business to force it in one direction as opposed to the other. Yeah, right. SN2 is nice. SN2, if you have a good leaving group and you have a good nucleophile, SN2 it's done, right? You're gonna get exactly what you want out. You know, yeah. But with SN1 it's not as good. Okay. Why don't I save this? There we go. Okay, it's saved. Yes.
Sorry to interrupt again, but I had a question about stereochemistry and SN1. So like for this one, there's no stereocenter or chiral center. So there's like nothing is subject to being inverted. But in the SN2 example, there was chirality involved. So like, is that just the nature of SN1 where it's not really constitutive of like stereochemistry changes?
Yeah, that is a super important question. I did not remember to bring that up. That matters a lot. So SN2 retains stereochemistry, or rather, it inverts stereochemistry, but like with SN2, right? So if you start with like something like this, right? And you, I use bromine a lot because like it's like the easiest example. Everyone's always familiar with bromine. But okay, let's say you have this, right? And you have, I don't know, whatever was a good nucleophile, right? Let me scroll up, see what we had. Okay. Let's use azide because it's just azide should actually probably be higher on the list. It's a really good nucleophile. So okay, let's put it there, right? And then this is happening in whatever solvent it's happening in. There's a little bit of discussion about solvent when it comes to this, right? But like we generally want to pick a polar aprotic solvent, right? So for example, what is a good one? Dichloromethane is a good polar protic solvent. DCM is dichloromethane, whatever. This is like a fine point that they might mention in like the lecture details. But in general, we're not too worried about solvents, right? So, okay, when we do this, the point is this happens, right? But now when we do SN1, and I'll use maybe a slightly different example, right? So if we start with, let me pick a new molecule. Right. So we can start with something else that's a nice leaving group. So OTS, O-tosyl is a good leaving group. You'll see what that one is in lecture. It's a really, really good leaving group. It's a very nice one. And well, okay, that could be a hydrogen, right? That's fine. Okay, and then we put it in, oh wait, no, wait, we want it to be a tertiary carbon, don't we? Right? Yeah, okay, so we're gonna give it a methyl instead, right? Just leave it as is. All right, and okay, and we're gonna put it in with, I don't know, a nice nucleophile, so we can put it in with H2S. Okay, and this has to happen in a polar protic solvent. So actually, okay, I'm just gonna use water. Water will be both the solvent and the reactant here. So water, and well, what happens is we lose stereochemistry because we have to go through a carbocation. Okay. So there is, because we have to go through a step here where we lose stereochemistry, right? We lose that information. At the end, we can only have it be racemic, right? This is still a chiral center. Yeah, because it has 4 different things on it, but this has to be racemic at the end because we had to go through a state where it was achiral. Anytime you're going from something that's achiral and your product has like chiral centers, it's chiral, you have to get a racemic product out. Yeah.
Wait, can you say that again?
Yeah. So in general, right? So in general, if you're going from something that's achiral, well, in this case, you're going from chiral here, right? And then it's an achiral intermediate, right? Because over here, this is sp2, this positive charge, right? Or in other words, it's just flat. And this OH here, if this thing is flat, the OH can come in either from the top or from the bottom. And depending on which it does, it'll make a different thing, right? Or in this case, we wind up having a totally flat molecule with a methane or a methyl, ethyl, and propyl group, right? 1, 2, and 3 carbons in each of the spots, or whatever else we have. The water, the H2O, can either come in from the top or from the bottom, either one of the two. So we're starting with something that's chiral, but we're going to an achiral intermediate at this carbon, right? In theory, there could be other stuff somewhere else on the molecule, but we're not worried about that, right? That other stuff is going to stay as is. We're not touching it, right? So it goes to achiral, and then whenever you go through an achiral step, you have to get out a racemic product. Or your product could be achiral, but in this case, it's not, right? If you're making a product that just doesn't have any chiral centers, then okay, it's going to be achiral too. That's just because it has no chiral centers, right? But if you get a chiral center out at the end, then it has to be racemic because you didn't have any information at this step, right? You lost it.
So like what would be the advantages of wanting to choose SN1 if you're not in control of the stereochemistry kind of as how you would be in SN2? Or at least like you can know what you'd get out for SN2.
Yeah. SN1's not a great reaction. It's really not. You can't control the stereochemistry. And in real like chemistry, stereochemistry matters a lot. It makes a huge difference. In general, it's better to avoid SN1 reactions because they're harder to control, right? They do this. They involve a carbocation, which can get messy. It's not like a good reaction. Occasionally, though, you have a tertiary substituent, and there's no other option. Or this is another one of those situations where allylic and benzylic are also still really good, right? So if you have a secondary benzylic substituent, right? Like here's an example that I got wrong on a test once, just for fun, right? So here we go. So we have something like this, right? And then we have, I don't remember what it actually was, right? But like, if it's like a bromine, right? And you put this in water, this is gonna go by SN1. It's gonna become this, right? And now I skipped a few steps now, right? The bromine has to come off, the H2O has to come on, and you have to pluck off a hydrogen. But this will happen by SN1, right? Because doing SN2 on a secondary carbon is already pretty iffy.
Oh, I see.
Yeah. So in this case, this would probably be by SN1,
Mm-hmm.
right? Yeah. Yeah. In general, you usually don't want to do SN2, SN1. It's generally preferable to stay with SN2. Yeah.
Thank you.
All right. Well, let's really run through the problems. Yeah. So okay, we've talked a lot about what you're gonna see coming up next week, or I guess this week now, right? These problems are mostly about stereochemistry. So, well, this is like old news, but hey, we'll go through them. Okay, here we go. So let me screenshot, copy. Oh yeah. Okay. Oops, there we go. Oh my God. Okay, I just want to move this, that's all. Okay, here we go. Okay, so here's the question. It's widely known that only a few radical halogenation reactions are used in practice. Okay. So we want to prepare neopentyl chloride from neopentane, okay, and cyclopentyl chloride from cyclopentane. We haven't focused on naming, so let me draw those out. Okay, so what we want to do is take this and then stick a chlorine on somewhere, and we want to take this and we want to put a chlorine on somewhere. Okay, what structural feature of these molecules makes this possible? Okay, I will ask you guys because, well, yeah, why should we chlorinate on these molecules? Like what is the benefit here? Or what is nice about these molecules that makes it easy or good to chlorinate them?
Well, usually chlorine is really reactive. So for these molecules, you have secondary positions where you can chlorinate. So you won't get like a very weird ratio of products where chlorine is kind of in different places. Like it's going to be at the secondary position.
Okay. So I guess, so in this first one, we only have primary hydrogens, right? But I guess you mean in the second one, right? It'll only be in the secondary position. That's right. But I mean, I drew the chlorine over here, but why didn't I draw it over here?
Would it even matter in this situation? Technically, we could draw it anywhere in that ring.
Yeah, right. So we can put it wherever we want on this ring. another way to say this is that, well, look at all of these hydrogens, right? I mean, they are different hydrogens, right? Like clearly, I mean, this hydrogen and this hydrogen are not the same thing. They're two different real hydrogens that are like next to each other, right? But they're basically, I mean, as far as we're concerned, they're gonna react the same, right? Wherever we put that chlorine, we can just twist the molecule or flip it upside down or something, right? And we can always draw it to be in this position, right? So those hydrogens, what I was saying about them, they're like physically they're not the same, but more or less they're kind of in like the same positions as far as we're concerned, right? And I mean the same goes for this molecule here, right? So here's all these extra hydrogens, and well, let's say that I'm this hydrogen right here, right? And I'm gonna zoom in. Okay, maybe I don't want to zoom in that much. Here we go. Let's say that I'm this hydrogen right here, right? All I can see is, well, all I can see is this carbon and these other hydrogens, right? Like that's about as far as you really get, right? Can I, if I was this hydrogen, would I be able to tell the difference between being this one or this one? No, right? As far as they're concerned, all that they can see is the same thing, right? This is or to put it another way, I mean, you could twist this whole molecule, and wherever you put the chlorine, you could always twist it so that you get the same thing as however I drew it. Yeah, if we want to be really abstract, right? So, okay, I mean, we have this, right? If we want to be really abstract, we say that there's symmetry in the molecule, meaning that all of these hydrogens are like to the same, right? We can rotate the molecule and we can move all the hydrogens to the same place. So in some sense, there's kind of the symmetry. There's sort of another idea at play here. There's also this idea of like hydrogen environments, right? And this is not a term that you've heard yet, so I don't worry about it too much. I think I'm pretty sure. So if you're taking the class now, I'm pretty sure you have to be taking organic chemistry lab too. And this is something that. Oh, you don't?
No, like chemical engineering, I have to take this, but not orgo lab. So.
Oh.
A lot of us are not taking it.
Okay, so maybe not. Okay, so maybe you aren't, but I know in orgo lab this is something that that I think you'll be covering fairly soon when it comes to time to talk about NMR. This idea of hydrogen environments, which is that all of these hydrogens are in the same environment, right? Is that if you're this hydrogen here and you look to your left or to your right or all around you, you will see the same thing as the other hydrogens that are there. Okay. This is kind of like a vague idea, right? This is like a pretty abstract idea that I'm saying. So I guess I do want to pause and just ask, like, do you see what I'm talking about? Does anybody not? If you're confused, ask questions, please. Okay. Okay, it seems like you guys are on top of it. Okay, so here we go. Here's the next question. Let's copy and paste it in. Oh, oops. There we go. Copy. Okay. This is kind of just like a definitions question, and it's good to keep these in mind because there's a lot of these definitions, and well, it's hard to keep track of all of these things. Here we go. Let me draw. Okay. Whoop, there we go. Okay, fill in the blanks with the appropriate type of stereoisomer. All right, this picture's a little blurry. Do the compounds have the same molecular formulae? No. Okay, they're not even different. They don't even have the same formulas. So okay. Well, these are just different compounds, right? They're different altogether. There's not a lot more that you could say that about them that's like super informative. Let me. There we go. Right. So they're different compounds. Slash, I guess you could say they're not isomers. Okay. Here we go. Do they have the same molecular formulas? Okay. All right. Well, now they're isomers, right? Do they have the same connectivity? No, they don't. Okay. Now I'll ask you guys. What do we call it if they don't have the same connectivity?
Constitutional isomers.
Yeah. Okay. Yeah. Right. So they're constitutional isomers. Yes, they do. Then what do we call them?
Stereoisomers.
Stereo.
Okay. All right. And we're going just zooming through this whole thing. Can they be interconverted by rotation about single bonds? What if they can? Yes.
Conformational.
Yeah, there we go. Conformational. Okay. And no, then what?
Configurational.
Okay. Configurational. Okay. Is the isomerism at a tetrahedral center? So if it's not, then what do we call it?
Is it achiral or not?
No. In this case, no.
What does it mean by tetrahedral center?
Like sp3. So like one of these guys. The alternate being if it's like a double bond.
So like
Or-
cis and trans.
Yeah, so that's like one type of this isomerism. There are other types too, which like sometimes people love to talk about, which look like this, right? So if you build this like this big thing, right, of this whole flat thing, right, and then it was kind of ugly. Here we go, right? So I know in the lecture they like to talk about this, right? Let's say you put hydrogens here, right? One of these is going to come towards you and the other one is going to come away from you. There's another type of this. Actually, actually no, this isn't. I lied. Because this one you can change by rotating around a single bond. So no. Anyway, the point is these are geometric isomers. This is not the most important thing in the world, right? Okay, this is the one where it matters. Are they non-superimposable mirror images? If they are, what is it?
Enantiomer.
Yeah. Okay, and if they're not, then what?
Diastereomer.
Yeah. Okay, cool. Yeah, that's it. This is just like this is pretty helpful. It would have been good if we had this like last week, right? Because I mean, this is kind of one of those things where there's just a lot of like terminology and yeah. Okay. Whoops. Let me get the next problem. Okay, here it is. Let me move this thing up. Not that far up. Okay. Okay, label each stereocenter. All right. first things first, this is hydrogen is 4, right? We know that. Okay, bromine and sulfur, those are both higher than carbon. So, okay, we know that carbon is 3. Let's see. Which of bromine and sulfur is higher? Bromine is huge. Bromine is really large. And then sulfur is 2. Okay. Anybody want to tell me if this is R or S?
I think it's R.
Is it R? Okay, if we flip that hydrogen to the back, then we get, it's R.
Okay.
Yes. Okay. Again, you want to flip the hydrogen to the back and then see if it turns right or left. In this case, it turns right, so it's R. Cool. Okay. Let's draw in the hydrogen because that makes our lives a little bit simpler. We know hydrogen is 4. That's easy, right? Over here we have, I'm going to draw it all the way out because that's better. Okay. So, okay, hydrogen is 4, right? Here we have oxygen and then carbon and carbon, right? Oxygen is going to be the highest, so that's 1. So we have carbon and carbon, so we have to look a little bit further, right? This carbon has an oxygen attached. This carbon also has an oxygen attached. Damn, okay. Do you remember the rule for when you have double or triple bonds?
Double bond count as like twice
Yeah, okay.
as much.
Yeah, right. So as far as all that we're concerned about is, okay, we're going to take this and, well, we're going to write another oxygen in. Okay. Okay, and so now we have carbon. We have a carbon with 1 oxygen and a carbon with 2 oxygens. So the carbon with 2 oxygen wins, right? So this one over here is 2 and this one is 3. Okay.
Is that with any double bond or just oxygen double bonds?
Any double bond. Yeah,
Okay.
it's with any. Triple bonds too.
Is triple the weight or still double?
It's triple.
Okay.
Yeah. Okay. Anybody in, is this R or S? Somebody.
R.
R.
All right. I'll take your word for it. Or I don't have to, right? This H is sticking out front and the numbers go to the numbers turn the car to the left in this case, right? But the H is to the front, so we have to flip it. So really the car is going to the right. Huh?
Yeah.
What was that? I couldn't hear it.
Oh, yeah. I was saying it's basically like, since the H is sticking out into the front, it's basically like if the whole like the wheel part of it is facing, is behind it, so you have to turn it all the way around. So technically, it's S.
Yeah. Yeah. So you have to do the opposite of what the numbers say, right? So the numbers go this way, right? Which would normally be S, and then we flip that, so it's R. Or you just do this the safe way, and you actually just rotate the molecule, right? The ultra safe way is to build the molecule and then just do it that way. Yeah. Okay, let's see. Oh, if this whole structure is chiral or achiral, I don't think it's a surprise if I tell you this first one's chiral, the second one is chiral, right? This third one, is it chiral?
Achiral meso.
Yeah, meso.
Yeah, yeah, right.
But do you
It's
still then
achiral.
put the like R and S on the stereo centers?
Yes. Yes.
Okay.
So you still have R and S stereo centers, but it's meso. Well, okay, so let's actually look at each of these. Right? So here we go. There's an H back there and an H back here. Okay. H is the lowest priority. That's easy. O is the highest weight atom. That's easy too, right? And okay, this is a little methane group and this is a whole big group. So this is going to be 2 and 3. Is that R or S?
R.
Yeah, it's R, right? Okay, without even doing it, anybody tell me what this other one is? Whoops, I already told you it's S. Okay, sorry. Yeah, okay. This other one is S. right? The reason I knew that is because if they were both R, then when you flip them, they would both be S. And that's totally different, right? You can't do anything about it. But if you have R and S, right? And then you flip it around so you get S and R, what you could do is rotate this molecule and you'll get R and S again, right? That's why meso works. Okay, so that's instantly how I knew. So if you have this meso compound and one of them is R, then this other one is going to be S, right? That is probably too specific of a trick to like really remember and think on a test like, oh yeah, I have a meso compound with one R, it's got to be S, right? No, like probably not. But that's just a way that you can kind of like logic through it without doing all of the extra work on this one. Okay, here we go. Here we go. Is this molecule, let's start, chiral or achiral?
Is it achiral? Could there be like a plane of symmetry through the point that has the stuff sticking off and the one across from it?
Yeah, that is exactly it. The other way to think about it, if you look this way and this way, you see the same thing. Okay. So it's achiral, right?
Also, if you try to number it, you get stuck with 2 and 3. I guess it's the same thing, but
exactly, right. Yeah, right. So numbering this one wouldn't even really work, right? Or in general, if numbering something fails because there are two things that are exactly the same thing, then it has to be achiral, right? Because you need 4 different things. So numbering should never break like that. Okay, chiral or achiral?
I think chiral.
Yes, it is chiral. Okay. How many stereocenters?
2.
Yeah, okay. So there are 2 here. Cool. Right? So the one in the back also is, which is maybe a little weird at first, but if you look this way and this way, you find 2 different things, right? If you go down the chain. Okay, so let's look at this first one, right? Oh, this is an absolute mess. Okay. So here we go. Let's look. Okay, all right, okay. We have a hydrogen sticking out front. All right, that's easy, right? We can start off with that. So that's 4. Done. Okay, let's look. Well, if we look this way, this is the only way that we're going to find a chlorine, right? Everywhere else, we're just going to find carbons, right? So, well, we know that the first thing going down each direction is a carbon, right? So this chlorine is the first thing that's really heavy. So this whole direction is going to be 1. Okay. If we look up here, we have a carbon, right? But then we keep looking further and it's connected to 3 other carbons, which is a lot. While if we look this way, it's only connected to 1 other carbon. So this one is going to be 2. That leaves this one being 3. Okay. So, all right, well, we go, whoops. So we're going that way, right? So that corresponds to S, but the hydrogen is sticking out front, right? So this here is R. Okay. It was because the hydrogen was sticking out front. All right. Let me draw this molecule again. Right. So there's that hydrogen that's sticking back, and there's that chlorine. Okay. Hydrogen, easy, right? Okay, now this is the kind of interesting part. So we have to look down each chain, right? We look down this chain. Well, so each of them, it has a carbon, right? We know that. We look down this one. This is connected to 1 other carbon. That's not really special, right? Look down this one. Also connected to 1 other carbon. Not that interesting. We look up at that one. Okay, now this one is connected to 3 other carbons, right? So this is we go down the chain step by step, and this one is the most interesting at the first step. So this is going to be 1. Okay, that might be a little bit weird because, well, we would think that like, okay, that chlorine down the line is going to be heaviest, but no, we have to go. You go step by step. So this one, this over here is 1. Because now we go to these other 2, and now we go down the chain another step, right? And now this one has the chlorine and the other one doesn't have anything. So this is 2 and this is 3. Okay. So are we R or S?
R.
Yeah, that's R. Okay. Okay. Here we go. This next question is about Fisher projections. And if you remember, I think sometime last week I was like, yeah, there are these things, Fisher projections, but you're not going to talk about them until next year, right? Or until like the end of the 2nd semester of organic chemistry. That is still the case, and we're not going to go through these. I'll just give you a flavor of what this whole thing looks like with the first problem, right? So we want to draw R2-butanol, right? Okay, so here's that structure, right? Oh, whoops, that is in fact not the structure, right? So it looks like this, right? Except we want it to be R. Okay. Oh, is the carbon with the chloride attached not a stereocenter in 3E? Oh no. Yes, it is. It is, isn't it? Yeah, that would look like it is. Okay. We almost got away, didn't we? Here we go. So HCl, right? And then the rest of it looks like this, right? Okay. H is 4. That's easy. It's always 4, basically, right? Chlorine is 1, right? We look over here. This carbon's attached to a few more carbons, right? And this one's only attached to 1 carbon. So it's number 3. Okay. And then we do the priority ranking. And someone who's really good in 3D, do you know what this is?
Is it S?
Yeah, it's S. Okay. Think that one through, because now this one is weird to think about. Okay. This one involves some like complicated rotation. You have to rotate this molecule by like 120 degrees in this direction.
I do this thing with my hand that helps.
Wait, what thing?
Like, okay, here, let's see. Okay. If you like pretend that your arm is the hydrogen and you make this the 3, you stick your arm where the hydrogen is, like in the rotation of the paper, and then you can like look at it. And if you remember what you numbered your fingers, you can see the direction.
Ah, okay.
I
Yeah.
think my dad taught me that when I was younger.
Yeah. That's one that can work. That's one way. That's kind of like analogous to building a model, right? Because you build it as you see it on the page, and then you just can spin it around. That's another way that works. Yeah. I mean, this is sort of one of those situations where like whatever works for you individually is what you should use, and don't bother using anything else, because yeah. Yeah. Okay. So the idea here is, okay, we want to make this thing R, right? And well, we know that this is going to be 1. We know that this hydrogen is going to be 4, right? We know this is going to be 2 and this is going to be 3, and we want it to look like this. Okay, so we need this hydrogen to be in the back, right? Yeah, I went through that one fast. This is kind of a situation where you might want to just build both enantiomers and then figure out which one is R and S, and that's the one that you're going to work with. Okay. And I might have mentioned this before, but the idea with Fisher projections is that you draw them like a cross, right? And then this corresponds to something that looks like you're going back into the page, and then you're going out of the page on the sides. Okay. The way that I remember this is that it looks like a bow tie, right, with these dashes here. So I don't know. That's like a really crappy way of remembering it, but whatever. Yeah. So we want to draw like the interesting stuff to be in this kind of projection, right? So in this case, what we do is we look at this molecule from like above, all right? And what you would see in that case is you would see this methyl going away from you, right? You would see this ethyl also going away from you. And then you would see on your right, you would see a hydrogen. And then on your left, you would see this OH, right? And the way that we would draw this in the nice Fisher projection is we would draw a cross, HO, there's a hydrogen, and there's that other stuff, right? And over here, this is not chiral, this is not a chiral center, so we don't have to draw it as like a chain. Okay. Again, you will see this. It will come up. It will come up in a long time, but for now, this is we'll just do this one example just to show you what this is all about. Okay. And then here we go. The last question is I'm not even going to copy and paste it. Okay. So you have 85% R and you have 15% S. Okay. The question is, what is the enantiomeric excess? Okay. Right. And I will even be honest with you, I didn't remember the formula for enantiomeric excess, so it's not like this is not like the biggest deal. I should say I've never seen them ask a question where they ask you for enantiomeric excess, or I think there are some other formulas that you learned from it. I've never seen a question where they ask that. That being said, they like asking questions that nobody expects. So it's something that's good to know, right? This is kind of like me saying that the best way of taking the class is to know everything, which is not super helpful, right? But it's hard to say. My point is, if we're going by history, it's very unlikely that they'll ever ask about enantiomeric excess. But you know, they like to mix things up a little. Anyway, I had to look this up myself. But what you do is you do 85% minus 15%, and then you divide by the sum of them, right? And so hopefully they should sum up to 100, right? Because hopefully you should have 100% of your reaction. But this is 70%. Okay, that's it. Okay, cool. Yeah, that covers, that's the last of the questions. Again, this last one, not the biggest deal. That would be it. Okay. Let me stop share and then